Hello everyone, my name is Misiak and on the behalf of my co-authors Niko Wißmann, Arnulph Fuhrmann and Marc Erich Latoschik, I will be presenting our work on accelerating stereoscopic rendering. If we look at the requirements for classical desktop rendering and rendering for VR, there are a number of differences between these two systems. For VR, we need to synthesize a stereoscopic image pair. Our displays span a much larger field of view when compared to a desktop monitor. As a result, we have to render more of the scene at a much higher resolution if we wish to achieve the same pixel density. And of course, since we are substituting our entire field of view with artificial visual stimuli, VR rendering requires a much higher and more stable frame rate. If we combine all of these factors together, we arrive at a large performance gap between these two systems. To bridge this gap, new VR-specific rendering techniques have to be devised. Luckily, research is being done in both academia and industry to address this issue. One way of achieving a high frame rate is to exploit the constraints on human spatial-temporal vision. Existing temporal coherences between consecutive frames can also be leveraged to synthesize new in-between frames. Such techniques are already being used in the industry. Foveated rendering is a very active research area, with recent research focusing on efficient implementations of multi-resolution rendering and reducing perceptual artifacts in the periphery. Orthogonal to these approaches, VR rendering can also be accelerated by efficiently generating a stereoscopic image pair. Due to the small offset between the two eye positions, much of the information present in one eye can be reused for the other. Didik et al. Presented an adaptive grid warping approach for quickly synthesizing the second eye viewpoint. Reprojection errors are filled in by simple inpainting and by sampling previous frames. Schollmeier et al. Improve upon Didik's approach by introducing a more sophisticated inpainting technique and a new heuristic for adaptive grid subdivision. They also support the reprojection of semi-transparent materials. Our presented approach also aims at accelerating stereoscopic rendering. We share some core similarities to the work of Didik and Schollmeier, as we also employ an adaptive grid warping approach. However, we differ in a few aspects, the most notable being the handling of reprojection errors caused by disocclusion. To this end, we make use of hardware-accelerated adaptive ray tracing available on the latest GPUs and correctly reconstruct the missing information, a feat not achievable with common inpainting techniques. Adaptive ray tracing has been used to reconstruct reprojection errors before. In the work of Adelson and Hodges in the context of synthesizing animated frames in a fully ray traced environment, and by Vaya et al., who implemented a ray traced foveated rendering system. Okay, let's take a look at our rendering system's architecture. We start off by rendering the left eye image as usual using a standard deferred pipeline. Prior to submitting our finished image to the left portion of the output display, we perform a tone mapping pass. And that's basically it for the left eye. Now onto the generation of the right eye image. To this end, the left eye image as computed by the lighting stage as well as its associated depth buffer are forwarded to the reprojection pass. Here, the radiance information from the left eye is reprojected into the right view using an adaptive grid warping approach. The resulting reprojection will contain errors caused by areas not previously visible in the left eye. We detect these regions and discard the associated pixels from the output image. The resulting holes are then filled with correct information in a subsequent ray tracing pass. And finally, the finished reprojected image is tone mapped and submitted to the right portion of the output display. It should be noted that our reprojection algorithm does not depend on any specific rendering pipeline, and the reprojection can also be made from right to left. Alright, so in the following we will take a closer look at the reprojection and hole filling passes, since these are the more interesting ones. First off, let me briefly explain how grid warping works as a reprojection mechanism, since it has already been mentioned a few times during the presentation. Let's assume we have the color and depth information for viewpoint A, which is in our use case the left eye. We use it to displace a grid of n times n vertices and map the color texture onto the surface of our grid. The grid mesh is then simply rasterized from viewpoint B to obtain our reprojected image. Now obviously, the reprojection quality is primarily dependent on the grid's resolution. Ideally, we would like to use a grid with the same resolution as our input image. So for an HD image, this would be 2 million vertices and 8 million for a 4K image. However, such a high number of vertices can itself become a limiting factor, and practically it is not even necessary, as many vertices can be warped together. Therefore, it is a better idea to rather subdivide a grid adaptively based on the underlying depth image. However, the question now becomes, how do we decide which grid cells need to be subdivided? Which brings us to the first step in our reprojection path, the compute subdivision heuristic. Didik et al. Subdivide a grid cell if the difference between the maximum and minimum depth values inside cross a certain threshold. Schollmeier et al. Employ a collinearity measure where a cell is subdivided based on the curvature formed by its depth values. Both of these approaches operate solely on the depth values and don't consider the limitations of the human visual system. Our subdivision approach, on the other hand, is specifically aimed at stereoscopic rendering, as it is based on binocular parallax and evaluates depth discontinuities in relation to the distance at which they occur. A quick detour to binocular parallax. If our eyes converge onto a point, they rotate inwards and their lines of sight cross at that specific point. The angle, which is formed by the crossing lines of sight, is referred to as binocular parallax. It depends on the interpupillary distance and the distance of the convergence point. It plays a significant role in depth discrimination based on stereoscopic vision. Let's say we want to differentiate between the depths of 2 points, A and B. For this, we have to consider the binocular parallax of converging on both points. If the difference between the angles alpha and beta is above a certain threshold, delta, we can discriminate between these two depths based on stereoscopic vision alone. The threshold value delta is also referred to as stereoacuity, and for a major part of the population is in the range between 0.5 and 1 minutes of arc. The rationale behind our subdivision heuristic is basically, if a grid cell contains depth values which are not discriminable by our stereoscopic vision, we don't have to subdivide a cell, as its reprojection will result in the same perceived depth information a planar unsubdivided cell would deliver. For a conservative estimate, we compute the min-max depth values in a cell, from which we calculate in the binocular parallax. If this value is above our threshold, we mark the cell for subdivision. Let's see this heuristic in action. On the left, we see a visualization of the user's position as he moves through the scene. The user's viewport is shown on the right with a wireframe rendering of the adaptively subdivided warping grid. We can observe that grid cells which were previously not subdivided, for example the area around the door frame, become subdivided as the user moves closer, increasing the binocular parallax difference. Once the grid cells are marked, the subdivision can take place. We implemented this step with the help of the hardware Tessellator, as it offers a superior performance in comparison to a geometry shader. Each marked grid cell is tessellated only once and with a factor of 16. When applied to our starting grid resolution of 16 × 16, this results in a one-to-one mapping between vertices and pixels. With the correct subdivision, the grid can be reprojected into the viewport of the right eye with the mechanism described earlier. One prominent artifact of a grid reprojection are so-called rubber sheets, which wrongly connect surfaces at depth discontinuities. They can cover regions which were previously not visible in the left eye image, as well as occlude regions where correct information was available. Therefore, our next step in the pipeline is to detect and discard the affected fragments. Details on this can be found in our paper. The resulting holes in the reprojected image now need to be filled. This happens in our next and final stage. One simple way of solving this problem is by choosing the color of a random neighboring fragment. While very efficient, this method is only suitable for filling in very small regions. Schollmeier et al. Implemented a more sophisticated in-painting solution using a low-pass filtered intermediate images. However, the core limitation remains. No new information which was previously hidden can be synthesized this way. So instead of hiding the reprojection errors, we chose to correctly reconstruct them. To this end, we use an adaptive ray tracing approach implemented using the new DirectX ray tracing API. On supported GPUs, the acceleration structure traversal and triangle intersection tests are then performed on dedicated hardware and in parallel to rasterization. Implementation-wise, 3 new shaders are required: a ray generation, closest hit, and a miss shader. The ray generation shader dispatches primary visibility rays for fragments which have been discarded in the previous step. The hit shader simply executes the same shading code as our lighting path for the left eye image, while the miss shader just simply samples the background color. Unlike in rasterization, a single ray cannot compute the gradient of the texture coordinates at a specific point. Therefore, we resolve to a cone footprint approximation for selecting the MIP level during ray tracing. Here we can see the differences in texture MIP levels between regular rasterization and the cone footprint approximation. In addition to the ray tracing approach, we also implemented a second hole filling method based on regular rasterization. The missing fragments are reconstructed by simply re-rendering the scene from the right eye's perspective. To achieve a speedup over a naive stereo rendering, the fragment shader is only evaluated for the discarded regions. We did this as we wanted to compare the hole filling performance of the dedicated ray tracing hardware against the GPU's rasterizer. Let's have a look at the performance evaluation of our algorithm. We did our benchmarks on 4 popular test scenes. We chose these scenes as their complexity regarding geometry, textures, and lighting is somewhere in the ballpark of modern computer games. Our test hardware consists of a modern CPU and a powerful recent GPU with ray tracing acceleration. For the benchmark itself, we measured the total time it takes to render 1000 frames on a predetermined camera path. We benchmarked all scenes in 2 resolutions, HD and 4K. Our 3 test systems were Plain Stereo, which is our reference system, Repro Re-Raster, our reprojection algorithm with rasterization-based hole filling, and Repro RT, which is our reprojection algorithm with ray trace hole filling. The total time encompasses the costs for rendering the left eye and the reprojection step. The 2 main results are the following. Reprojection is almost always faster than naive stereo rendering. The only exception being the bistro exterior and night scenes in HD, where the re-raster system actually performed worse than plain stereo. The second finding, the Repro RT system outperformed the re-raster system in all instances, achieving speedups ranging from 28 to 55% in comparison to plain stereo. Here is a breakdown of the individual render stages for both reprojection systems in the bistro interior scene. The first 2 passes belong to the left eye image, followed by the reprojection stages, which are performed under 1 millisecond for HD and under 2 milliseconds for 4K resolutions. The following figure shows the hole filling performance of both systems in more detail. Ray traced hole filling clearly outperforms the re-raster system and is on average 0.15 milliseconds faster for HD and 0.5 milliseconds for 4K. These differences are even higher for the other scenes, as bistro interior could be considered a worst-case scenario with many simultaneous disocclusions. In conclusion, we presented a hybrid reprojection-based rendering system to accelerate stereoscopic rendering. We achieve a significant speedup over a naive stereo rendering while introducing negligible loss in quality. Our system leverages modern hardware-accelerated ray tracing and can be easily implemented into an existing rendering pipeline. In terms of limitations, we are currently reprojecting only opaque, diffuse surfaces. While specular materials can also be reprojected, their stereoscopic highlight disparity is not preserved. For future work, we would like to test our system's performance in animated scenes. We are quite optimistic in this regard, as the DirectX ray tracing API, which is responsible for the BVH updates, is targeted towards highly interactive applications. In addition, we would like to evaluate our system's quality on a perceptual level. Thank you for your attention, and keep an eye out on our publications page, as we are planning to release the source code of our project shortly.